Okay, so numbers what?
13 and 19.
13. Okay, start with that. 13. Okay, interesting problem, interesting problem. 13 and 19. Okay, so we have the integral of the square root of, and then we have um, x squared minus 9 inside the radical. Ugh, stop doing that here. Okay, so maybe the first thought might be to try and do substitution. It feels, I don't know, it just feels like a natural thing to go to. But that would be problematic, right, to approach it that way. Because if we let u equal this part in here, that normally works, but then its derivative would only be something in the power to the x to the power of 1 kind of range. And we do have x cubed over here, but that's just not going to work out, right? Well, first of all, the x is in the denominator, right? X to the power of 3, so that's not gonna be useful. So we're going to have to rely on the hints that this section has given us, right? So this section has given us some hints that work out in some cases, not always, and they're not always perfect, but we gotta try it out, right? So at the beginning of this section, how do I get to the beginning of this section? Here. Oh, this looks even better. So here is 7.3. So at the beginning of this section, we are given this little list of things that work out well. When we see something of the form square root of a constant squared minus x squared, try this substitution. When we see a squared plus x squared inside a radical, try this substitution. And when we see x squared minus a squared, where this is a constant, try this substitution, right? Okay, and where the given domains of theta, of the angle theta, are constrained by these conditions here. So this is to guarantee that the function is 1-to-1, and then we can do the substitution. Okay, once we make that substitution, then they're kind of hinting for you that these identities are going to become useful. Good. So given the problem we're working with, it seems like this one is the one that would best kind of fit. And in fact, example number 1 is pretty similar to what we're working with, right? Anyway, so let me write that down. Number 13 is, I'm not going to want that. Okay, so this is chapter 7, section 3, number 13. And we have the integral of, and we have x squared minus 9 inside that root, all over x cubed dx. Okay, and by this is the big hint right here that we should be using this substitution in order to see if this works out. And the restriction is that theta must be either in quadrant 1 from 0 to pi over 2, that's quadrant 1, or from pi to 3 pi over 2, that's quadrant 3. Either in quadrant 1 or quadrant 3 to make the function substitution, to make that a 1-to-1 function. Okay, so we just kind of proceed with that in mind. Let's let x equal to a, which in this case is a 3. Right, so let me rewrite that this way. This is x squared minus 3 squared inside the square root, all over x cubed dx. So we want this to be equal to 3 secant theta, right? And so theta is either in quadrant 1, or theta is in quadrant 3. Okay, so once we have that, then we can find our derivative. d theta of the x, make a block there, is equal to d theta of the 3 secant theta. On the left-hand side, well, that's just going to be dx d theta equals to this, which is just going to be equal to 3 secant theta tangent theta. Good. And so dx is equal to 3 secant theta tangent theta d theta. Good, 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 good. Okay, so how does this help? Well, we can focus on just the numerator for a second. We have that the numerator was x squared minus 9, and we're going to substitute our newfound value of x. So x right in there, come on, right in there, is going to become 3 secant of theta, and then all of that gets squared, minus 9, and we have the square root of that. Then that becomes 9 secant squared theta minus 9, all inside the radical. We can factor out the 9 and get 9 secant squared theta minus 1 inside the radical. And so now we can use our substitution, our identity, to replace this part right in here is equivalent to just tangent squared theta using one of our identities. And so this becomes equivalent to the square root of 9 times tangent squared theta, which then just becomes 3 tangent theta. And note that, well, okay. Let me take one more step here to make sure that this part is clear. I'm going to separate this here. The 3 is fine, right? The square root of 9 is 3. I'm going to leave this alone and do this. So taking some number that can be positive or negative and then squaring it always makes it positive, and then taking the square root of something that's always positive is equivalent to the definition of the absolute value of tangent of theta. Good. If we have some number, any number, and you square it, and then you square root it, these two operations will always be equivalent to taking the absolute value. Right? That's one of the definitions. That's one way to define an absolute value. Good. So think of what happens when you insert, say like we insert a negative 3. We make it a positive 9. The square root of positive 9 is positive 3. Right? If we insert a positive 3, it becomes positive 9. Square root of positive 9 is positive 3. So no matter what you input, the output is always positive 3. That's the definition of an absolute value, right? Whether you start off with a positive or negative, the output is the positive. Good. So these two operations become the absolute value of theta. However, tangent of theta is always positive. Tangent of theta is always positive in quadrant 1 and quadrant 3. Right. Remember that in quadrant 1, tangent of theta, which is sine of theta over cosine of theta, in quadrant 1, both sine and cosine are always positive. So therefore, this thing is always positive. And in quadrant 3, sine of theta and cosine of theta, sine of theta is always negative, and cosine of theta is always negative. Therefore, the negative over negative cancel, becoming positive. This thing is always positive. Therefore, it's not needed. These absolute value symbols are unnecessary. In quadrant 1 and quadrant 3, if we just allow theta to only be in those quadrants, then we don't need the absolute values because we're always going to get a positive answer. Right? For 0 less than or equal to theta less than or equal to pi over 2, pi less than or equal to theta less than or equal to 3 pi over 2. Good. So that's how we just kind of get rid of the absolute values. Any questions so far? Okay, so we have all the tools necessary now to come back to our original integral up here. This original integral over here, and replace each one of these things. So now I'm just going to go right over here. So after all that work, we saw that the numerator, I'm going to copy this integral of x squared minus 9 all over x cubed dx. So we saw after all that work that this whole thing just becomes 3 tangent of theta. Good. And we saw after a little bit of derivatives there that this part here, just the dx, becomes 3 secant theta tangent theta d theta. Good. That's just the dx. And we know the value of x. X is 3 secant theta. So we're going to replace this with 3 secant theta cubed. Good. So I'm going to make all those replacements and find a new integral that is going to be equal to 3 tangent of theta all over 27 secant cubed theta times another 3 secant theta tangent of theta d theta. Good. Okay, so now this and this become 9, and there's a 27. So all of that reduces to just having 1/3. So I'll write that 1/3 out here. Integral of. Okay, and then there was a power of 3 here, and there's a 1 there. So this secant and this cube cancel to give you just a squared. And so we end up with tangent of theta squared. So that's this tangent and that tangent becomes squared all over secant squared theta d theta. Okay. Okay, so let's break this all down into sines and cosines, and maybe hopefully some stuff will cancel. So tangent of theta squared, this part by itself is sine squared theta over cosine squared theta. And then the secant squared is 1 over cosine squared theta. And whenever we have a fraction, where we have a fraction in the numerator, a fraction in the denominator, we multiply the numerator times the reciprocal of the denominator. And so this becomes 1/3 integral of sine squared theta over cosine squared theta times cosine squared theta over 1, right? So kept the numerator and then flipped the denominator, d theta. And now these guys clearly cancel out, giving me just the 1/3 integral sine squared theta d theta. Good. And now we use our power reducing formulas for from trigonometry. And remember that we have 2 of them, obviously, sine and cosine. So for cosine squared theta, it's equal to 1 plus cosine 2 theta over 2. And for sine squared theta, it's equal to 1 minus cosine 2 theta over 2. So that's the one we're going to use. Little box here. This is from trig. Fun with trig. So this becomes 1/3 integral of, and then we have the 1/2 I'm just going to write it this way, 1 minus cosine 2 theta d theta. Pulling out the 1/2, I'll end up with 1/6. 1/6 integral of 1 minus cosine 2 theta d theta. Now we're ready to go. This is going to be 1/6, and then this is just going to become theta minus the derivative of cosine is going to be sine 2 theta, sine 2 theta. So kind of guessing and checking, the derivative of sine 2 theta is cosine 2 theta times 2 using the chain rule. So we have to introduce an extra multiple of 1/2. Good. Plus a constant. And then that's a pretty good place to stop with this, unless you wanted to factor out the 2. Factor out the 1/2 or distribute the 1/6. So let's distribute the 1/6. We end up with 1/6 theta minus 1/12 sine of 2 theta plus c. Good. So we're almost there, except the original question was about x, right? Not theta. So we have to go back to our description, right? So using that x was equal to 3 secant theta, we can solve for theta. So this is equal to x divided by 3 equals to secant of theta, which means that x divided by 3 is equal to 1 over cosine of theta, which means that cosine of theta is equal to 3 over x. So theta is equal to cosine inverse of 3 over x. So that's good. Or, I mean, we could just leave it here. And from this stage, say secant of theta equals to x over 3. Therefore, theta equals to secant inverse of x over 3. So if you want to write it in terms of secant, that's fine. Or if you want to go back to basics and rewrite it in terms of cosine, that's fine as well. Good. Okay, so all that's left is for us to replace each of these thetas with that. So this becomes 1/6 times secant inverse of x over 3 minus 1/12 sine of 2 times secant inverse of x over 3 plus some constant. Wait a minute. Did I do something weird? You know, I mean, this is right, but we could do better. We could do better than this, I think. Secant 2 theta. Okay, so let me box this up, but we could do better than that, right? Because we have a sine and a secant, so it's ugly. It's a valid answer. It's just pretty ugly. And I think we can do better than that because we have this, so we can create a triangle. In fact, after we've done this, we've solved for cosine of theta equals to 3 over x. So if we create our triangle, let's create our triangle like this. Create our triangle. We'll be able to have that cosine of theta is equal to adjacent over hypotenuse, like that. And so there'll be a missing value a over there. So 3 squared plus a squared must be equal to x squared. So a must be equal to the square root of x squared minus 3 squared. Or a equals to the square root of x squared minus 9. So that's what this is. Square root of x squared minus 9. Okay, so then now sine 2 theta, using another one of our identities, this is equal to 2 sine of theta cosine of theta. Okay, one of our double angle identities. So this is equal to twice sine of theta. Sine is opposite over hypotenuse, so that'll be square root of squared minus 9 all over x times cosine of theta, which is 3 over x. Good. So 6. This will be equal to 6 square root of x squared minus 9 all over x squared. So we can go back to here. We can go back to here and either stop there where I kind of replaced the theta and I replaced the theta. But that's kind of ugly, so let's go back and instead say let's replace the theta from there. So that'll be equal to 1/6 sine inverse of x over 3 minus 12 times, and then this sine 2 theta we established is also equal to 6 square root of x squared minus 9 all over x squared plus some constant. So the 6 and the 12 reduce to give you a 1/2. So you get 1/6 sine inverse of x over 3 minus 1/2 square root of x squared minus 9 all over x squared plus some constant. Questions, 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 questions? Any questions? Any questions? Any questions? Any questions? Good, 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 good. So these are long. So we'll make some fun. And let's see, how does that compare to number 19? The other one we had a question on. Number 19. Okay, so we have something that fits the form of, they suggested to let x equal to tangent of theta in order to solve that. It fits the form of a constant plus x squared. Right? This one fits this form. This one. If we have a constant squared plus x squared, the suggestion is that you should let the x equal to a tangent of theta and see where that takes you, right? So there might be a better way to do it, you might be thinking, but let's try this just because we're in this section. So someone might see this and think, oh, why not do a u substitution, right? Because it seems like the derivative would involve an x to the power of 1. And you're like, there it is, it's right there, right? But not quite, because it's not really x, that's 1 over x. So you're close, it's just not quite there. So it's possible to continue down that path, but it's complicated. It's not going to be a straightforward answer. If the x was up in the numerator, like outside the root, if it was x square root of 1 plus x squared, that would be that would be useful. Or like this one, number 17, here the x is up in the numerator. So if we let u equal to x squared minus 7, its derivative will be right there. give or take a constant, so it'll be a little bit easier. Does that make sense? Questions, 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 questions? Everyone sees why number 17 is a lot easier than number 19, even though they look very similar. The fact that the x is up in the numerator makes a big difference. Good. All right, well, since it's not quite as easy as just the substitution rule, we got to follow their lead and proceed by letting x equal to 1 times tangent of theta, or just tangent of theta, and proceed from there. Whoever asked about both of these, would you like me to move on with number 19, or do you think that you've got enough to kind of get started with it and see how you do with it?
Maybe if you go on a little ahead, because I got stuck in one part, and
Okay.
yeah.
All right, no problem. So this one is chapter 7, section 3, number 19. And we have the integral of 1 plus x cubed, x squared, and then all over x dx. Okay, so per their instructions, it seems like maybe we're going to try letting this be equal to tangent of theta. Figure out what that is. So d theta of the x is equal to d theta of the tangent of theta, which, okay, well, this is just dx d theta, is equal to secant squared theta. So dx equals to secant squared theta. All right, so we have a value for that guy. We have a value for that. Okay, so now let's figure out what's going to happen with this root. So if we have a root of 1 plus x squared, that's going to become 1 plus the root of tangent squared theta. And so we can replace that with the square root of secant squared theta. So that's just going to become absolute value of secant of theta, right? Something squared and then square rooted is an absolute value. Okay, but then that's when we come back over here and point out that back when we defined x equal to tangent of theta, we needed to restrict the domain of the theta value. It couldn't be just anything at all. And theta is restricted to be between negative pi over 2 to positive pi over 2. Good. So in that, in those two quadrants, this is going to be quadrant 4 and quadrant 1. Is the restriction of this. We have a one-to-one function for theta in that region. And so in that region, cosine is always positive. So therefore, secant is always positive. Right? In theta between negative pi over 2 and positive pi over 2, secant theta is always positive, so we just don't need the absolute values, right? They're redundant. So if I stick to theta in this region, it's always positive anyway, so why do you even need absolute values? Good? Okay. All right, so now we have everything we need. We're ready to go. We're going to completely substitute this. The numerator just becomes secant of theta. The denominator is tangent of theta. And the dx is secant squared theta d theta. Oops. There's a d theta there. Questions, 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 questions. Okay, so now let's bring this together and say that this is the integral of secant cubed theta over tangent of theta d theta. Well, what to do? If we're doing like a u substitution, then we can like u equal to tangent. Its derivative would be secant squared, so that would be good. But then we'd have an extra secant running around. Seems unhappy. So instead of bringing this together, we can take advantage of our substitution one more time. We know that secant squared theta equals to 1 plus tangent squared. Does that help? If we replace this with 1 plus tangent, we'll end up with secant tangent in 1 plus, and then secant tangent squared, secant tangent in the other way. All right, let's try that. Right, so you just try different things. You know, it's perfectly common and normal, and it's just the way it goes. You try something, it doesn't work out, you kind of back up and try something else. So maybe I should, you know, I'm backing up here. I brought them together and I thought, well, maybe that'll work, but kind of changing my mind and not doing that. Instead, I'm going to replace the secant squared with this. I'll end up with the integral of secant of theta tangent of theta times 1 plus tangent squared theta d theta. Right, so I'm just kind of skipping that thing right there. Skipping over my initial trial. Okay, so now this gets distributed, and I'll end up with the integral of secant theta over tangent theta plus secant theta over tangent of theta times tangent squared theta, and then the whole thing is d theta. Okay, so a little bit of cancellation is going to happen here. This guy reduces with that guy, so I just have power of 1. And then I'm going to rewrite this as 1 over cosine of theta, and this is sine of theta over cosine of theta. So again, it'll be the numerator times the reciprocal of the denominator. Integral of 1 over cosine of theta times cosine of theta sine of theta. So I just end up with 1 over sine of theta in this term, which is going to be cosecant theta. And then over here we end up with plus secant of theta tangent of theta, and then that whole thing gets d theta. So this one's one of our standard ones, right? The derivative of secant of theta is secant theta tangent theta. So thinking about the antiderivative, kind of going backwards, I can see that this one's just going to be the secant of theta. And this one is going to be end up being 1 over sine of theta. This is the integral of 1 over sine of theta. I'm just going to go ahead and separate them, d theta, plus the integral of secant theta tangent of theta d theta, which is equal to the integral of cosecant theta d theta plus this secant theta tangent theta d theta. Okay, so now they're both standard integrals at this point. You know, at this point you just have to know your derivatives to be able to know this one. And this one, it's not about knowing your derivatives, it's just about memorizing that this is a standard one we run into. And so if you just, you know, kind of brute force memorize it, then that's fine. Otherwise, you'll have to remember a little trick to be able to figure out what this is. So if you don't quite remember what the answer is, then the little trick to figure out how to do this is to do the following. We're going to multiply it by a new version of 1, and that new version of 1 is going to be equal to cosecant theta minus cotangent of theta divided by cosecant of theta minus cotangent of theta. This is a new version of 1, so it doesn't disrupt the value of that. Right? There's still a d theta here, d theta. This guy here, I'm just going to go ahead and jump to saying that this is just equal to secant of theta. Oops. Secant of theta, right? The derivative of secant theta is secant theta tangent theta. Good. Plus some constant. Okay, so now this guy here, we're going to go ahead and distribute, and we end up with the integral of cosecant theta squared minus cosecant theta cotangent of theta all over cosecant theta minus cotangent of theta d theta. And now we do a u substitution on the denominator. So we're going to let u equal to cosecant of theta minus cotangent of theta. And du d theta, the derivative with respect to theta, of cosecant theta is equal to cosecant squared theta minus, and then the derivative of cotangent of theta is, oops, I'm off by a negative. Hang on, give me a second. I'm off by a negative because I need the derivative of secant. The derivative of secant is cosecant theta cotangent of theta. That. And the derivative of cotangent of theta is this one. This is going to be the cosecant squared theta. Does it have a minus?
Professor, isn't the derivative of cotangent negative cosecant squared?
So negative of cotangent.
Positive?
Yeah, that's why I'm off by a minus somewhere. So it ends up giving me that. This is crazy. Yeah, I'm going to do that. And then the derivative of... Oh yeah, it also gives you a minus. Yeah, okay. They're both give you negatives. I don't know what I was thinking. So the derivative of this guy also gives you a negative. And the derivative of this guy also gives you a negative, making it a positive. And that's when you flip them around. Okay, so then my du will then be equal to cosecant squared theta minus cosecant theta cotangent of theta. Good. And so now it's got to match this thing up here, d theta. Good. Okay, so now if I make that substitution, I don't know why I had a brain fart there. We end up with that. And then this whole thing in the numerator becomes my new du. Okay, so then this whole thing up here becomes my new du. Okay, so then this whole thing becomes ln of absolute value of u plus some constant, and then that u goes back to ln of, and then the u, which was cosecant theta minus cotangent of theta, right? Plus, and we already had that secant of theta from before, and we have plus some constant. Right? So I just brought this guy. Okay. Any questions about this so far? Okay, so we're almost done, except the original question was, of course, written in X. We had a bunch of X's running around. So now we got to come back and find a way to rewrite all of this using X. And so we go back to our definition for X, which was X equals the tangent of theta. And I can use a little triangle. X equals to tangent of theta, or I can just flip it around and say tangent of theta equals to x over 1. So here's my triangle. Here is theta. Theta is opposite over adjacent, so x adjacent is 1. So this side is missing h. So it must be true that 1 squared plus x squared equals to h squared. So the square root of 1 plus x squared equals to h. That's going to be the square root of 1 plus x squared. Okay. So let's go through and replace each one of these. So cosine, that's 1 over sine. So let's think about sine. Sine is opposite over hypotenuse. So it'll be the other way around. Square root of 1 plus x squared over x is this guy. Cotangent is adjacent over hypotenuse. So this would be minus 1 over x. Plus the secant. Now secant is usually adjacent over hypotenuse. Cosine is adjacent over hypotenuse, so the other way around. You just end up with the square root of 1 plus x squared all over 1, plus some constant. Good, 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 good. Well, we could just combine those into one big happy fraction. ln of the absolute value of 1 plus x squared minus 1 all over x in absolute values, plus the square root of 1 plus x squared over 1, which is, over 1, plus a constant. Any questions? No? We're good, we're good, we're good, we're good. All right. Anything else? Anything 7.4? Anything 7.5? Seven four. Let's look at 7.5 stuff. So, like I said, there's no new material on 7.5. They label it strategies, I think. Strategies for integration. Where are we? Strategies for integration. That's 7.5. So like I said, no new material. It's just a pause and let's review all the various techniques we have, and they give you a nice little table for all the known integrals. and we just used this one, right? So like I said, if you remember the little trick of adding, multiplying by a new version of 1, the proper, the perfect fraction that will help, then you can kind of do it from scratch. Or if you just remember that this is the result of the integral of cosecant of theta, cosecant x in this case, then that's fine. Then you're not required to show the work for that one anymore, since it's considered now one of our standard ones. Good. We just developed some of these guys, right? Some of these patterns were recently established at the beginning of I think this is like 7.2. 7.3, sorry. Okay, so they talk about some strategies: simplify if possible, look for obvious substitution. Okay, so they're just giving you strategies on how to proceed and what usually works. Little tricks about rationalizing. Sometimes that works out. If you rationalize the denominator, you end up with something useful. Look out for trig substitutions that can help. We know what to do when we have powers of a product of sines and cosines, tangents, secants, cosecants. We have those kinds of products. Just giving you different ideas, but there isn't going to be a perfect guideline that always helps you, because integration is hard and there's lots of little tricks, and sometimes it's really hard to find out or figure out how to integrate it. Good. Okay, so try something, see if it works. If it doesn't, try something else. Looking at our homework, are there any suggestions about anything? Any problems with any of them? Let's see, what did I assign for homework? Where is it? Let's just focus on, say, the first 10. Any suggestions on what to do in the first 10? Any hints? What did I assign in the first 10? Can't find it. Where would it be? Where would it be? Where would it be? Okay, well, let's just go to the canvas thing. I can't figure out where I left it. So homework and 1.5. Okay, so I assigned number 3, number 4, number 7, number 9, 3, 4, 7, 9, 10. Number 3. Any thoughts on what we should do there? What technique would help on number 3?
U substitution, maybe?
And what would you let the U be?
Y?
If we do a direct substitution of letting U equal to Y, then we'd end up with just changing. We'd end up with the root of Y, ln of, square root of U, ln of U, right? It wouldn't really change anything. If we let it be the square root of Y, then its derivative would be 1 over the square root of Y, which we don't have. If we let U equal to ln of Y, its derivative would be 1 over Y. It just doesn't quite seem like a good place to go. So maybe the integration by parts. letting u equal one of those two, like thinking of this as a multiplication of functions, right? And then letting one of the two functions equal to u, the other function equal to the dv. Yes?
That sounds sound.
I'm sorry, what?
No, that sounds like a good idea.
Sounds like a good idea. You want me to begin it? Are you guys okay with that? And I'm glad to do whatever you guys guide me to do, but of course, I don't know if we have a limited amount of time and lots of problems to kind of think about, so I don't know if this is one that you want me to move forward with, or should I keep going and talk about something else? Work on this one a little bit, set it up, or move on?
I think I can work on that myself.
Okay, cool. All right, so let's move on. And so I think another one was like number 4. What do we do in 4? Maybe try, if we can separate it into a sine squared x and then a sine, we'd end up with sine and cosine times sine squared. And then the sine squared, we can convert it into a 1 minus cosine squared. And then we'd have we can separate it into 2 parts, one that has nothing but cosines in it, and then times sine x dx. And then that's when we can let u equal to cosine, and its derivative would be sine, so we can do a nice u substitution there. Did that make sense for number 4? Or would you like me to do a little writing in there?
That makes sense.
Made sense? Good, good. Okay. Anything else in the first 10 that maybe you guys had trouble with? Anybody had issues, problems, questions, any suggestions on what to do? Any of these? What else did I assign? Let's just do one of them, I guess, in the first few. 9 or 7, 9 or 10. All right, somebody throw out a suggestion between 7, 9, or 10. All right, 1 second. I'll be right back. You guys think about it. 7, 9, or 10. Pick one for me to do.
All right, guys, which one do you want to do?
Seven sounds like my.
Which one's the hardest one here? You think 7's the hardest one?
For my money, yeah.
Okay.
Number 9 looks like
Anyone
we
else?
just do partial fractions.
Yeah, I overheard a little bit. Yeah, number 9 looks to me like a partial fractions decomposition kind of thing. So factor the denominator, figure out how to add or subtract fractions that are simpler, so that give you that, and then that breaks down into simpler integrals. So that should be okay. So it's either 7 or 10 look a little more interesting.
So please, can you do number 7?
7, okay. So what do we think about 7? E to the, now that says arctan y, which is the same thing as tan inverse, to the tan inverse y. Okay. Well, You just have to reach back in the memory file there and remember what the derivative of tangent inverse is, which is 1 over 1 plus the y squared is going to be its derivative. So it looks intimidating, but it's really not that bad if you happen to remember what that derivative is. Now, let me write that down. So I don't know if you remember way back in the day when you had to figure out what this is. Y equals to tangent inverse of x. So you had given this, tangent inverse of x, and you wanted to find the derivative. Find dy dx. And so in order to find it, you take the tangent of y equals to x, right? And then you have to find the derivative of this thing, right? So dot 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 dot. Okay, so work later, you find that given this y equals to tan inverse of x, that dy dx is equal to 1 over 1 plus x squared. Good. There it is. The derivative with respect to x of tangent inverse of x is equal to 1 over 1 plus x squared. Right. So the way to achieve this is right here. If we want to find y equal to tangent inverse of x, then what you want to do is move that tangent to the other side. So tangent of y must be equal to x by definition of what tangent inverse is. Good. And then you do implicit differentiation to both sides, and then you solve for dy dx, and that's how you get all this. Okay. All right. So then back to our problem. If you're armed with that, then it doesn't seem too bad to do this question, but it just kind of reaches back and has you remember that. Okay, so now we have Chapter 7, Section 5, number 7. And we have the integral of e to the arc tangent of x all over 1 plus x squared dx, right? But that's the same thing as tangent inverse, so we're going to let a u substitution happen here. Let's let u equal to tangent inverse of x. So therefore, du dx is going to be equal to 1 over 1 plus x squared dx. So let's push that over there. So du is equal to 1 over 1 plus x squared dx. And we're ready to go. We're going to say that this is the same thing as the integral of e tangent inverse of x times 1 over 1 plus x squared dx. Good. So now when we substitute, we're going to get that this is now equal to the integral of e to the u power, right? Replacing the u with that. And all of this is just going to become du. E to the u du. Good. Now was this, oh, I'm sorry, this was not, okay, so we had limits here, from -1 to +1. I didn't copy it right. So this is from -1 to +1. And if I had it my way, as I've said before, I would always label these with the variable. So this is from x goes from -1 to x goes to +1. So this is still in terms of x. So this is still this way and this way. But now when I want to do my substitution, now I have to think about what happens at each one of these things. Okay, so if you think about the graph of tangent, it looks like this, comes this way and comes that way and goes like that, right? And then there's these vertical asymptotes here at -pi/2 and another vertical asymptote here at +pi/2. Good. Normally we input an angle, right? Normally this is like a theta, it's an angle. and the output is a decimal value. Okay, in this case, when x equals to positive 1, let's go over here. When x equals 1, we have that u equals tangent inverse of 1. Good. So tangent of u must be equal to 1. That's what we have to say. Okay, so here is 1. We're looking for the angle such that tangent of that angle equals to 1. If you think about this as sine of u over cosine of u equals 1, this must be the case when sine of u equals cosine of u. Right? When are they equal to each other? Well, that's just at
Pi over 4, right?
Pi over 4. Pi over 4. Right? It's one of our standard triangles, one of our standard ones. Pi over 4 is 45 degrees. So when this is 45 degrees and this one is 45 degrees, you know that this is 1, this is 1, this is root 2. Good. So tangent of 45 degrees equals to 1. Okay, anyway, so that's going to be pi over 4. You know, at this point, once you get to this stage and you want to figure out what this is, you can just plug this into your calculator. Just make sure that you're in the proper mode, whether you're in radians or degrees. So if you type in tangent inverse of 1, then you'll get this. And then when x is equal to negative 1, we're going to have that u equals to tangent inverse of negative 1, which means that tangent of u must be equal to negative 1. And so that'll be over here. Right here is negative 1. And it's nice and symmetric, and it comes over here, and it becomes negative pi over 2. Okay, so my new limits of integration are going to go from u goes from negative pi over 2. I'm sorry, pi over 4. Pi over 4. Pi over 4. Negative pi over 4 to u goes to positive pi over 4. Good. Okay, so the integral of e to the u is just going to be e to the u. That's the beauty of this function. E to the u evaluated from negative pi over 4 to positive pi over 4, or just e to the pi over 4 minus e to the power of negative pi over 4. So that's good enough place to stop, or you can just punch it into your calculator and get a nice decimal approximation. Questions, 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 questions? Okay, so that one wasn't too bad. Let's look at the other one. 10, try doing integration by parts on this one. So try separating it into the product of two different functions. And we let u equal to 1 over x multiplied by x squared. And if we let cosine squared. Try separating it as 1 over x times cosine 1 over x squared. Try doing that, and I think that will lead to good things. U equal to 1 over x, and the dv equal to cosine 1 over x squared. I think that should work out. What else did I assign? 11, 13, 15. Man, I assigned a lot of stuff here. 11, 13, 15. Let's go over here. 11, 13, 15. Any thoughts? 11, 13, 15. So we have the classic square root of something squared plus or minus a constant. So one of our chapters, gave us some hints about what to do with these cases, letting x equal to either tangent of theta, or letting x equal to secant of theta, right? So there's a couple of different things that it was suggested for us to do. So that's what's going to work for number 11, I think. Letting x equal to secant theta, and then we end up with secant theta minus 1, which is going to be with the tangent squared theta, which means that for a particular section of the domain, we'll end up with a tangent, right? So that whole square root simplifies to just tangent of theta, right? And then we have to deal with this x cubed part out here, but things should work out nicely there. Here, again, this we ran into what to do when we had powers like this, powers of sines and cosines. Because this one is odd, I would peel away one of those, put it out here, sine of t. Then I'd have cosine to the power of 4t. Then we can rewrite that as sine squared to the power of 2, and sine squared equals to 1 minus cosine squared. So I can rewrite all of that in terms of all cosines, and then there's one sine out here, so I can let u equal to cosine, and therefore I can rewrite this into a nice u substitution that's easy to integrate. Did that make sense for number 13? Or do you want me to write some stuff down? We're good on 13? I'll take the silence to mean you want me to write something down. So this is chapter 7, section 5. This is number, 13? And it's the integral of sine to the power of 5 theta cosine to the power of 4 theta d theta. So I was just saying that what we could do is peel away one of these guys, put it out in front, and end up with sine to the power of 4 theta cosine to the power of 4 theta sine d theta. And then we can rewrite this as the integral of sine squared theta squared cosine to the power of 4 theta sine of theta d theta. Let's put theta in there. Good. And now sine squared theta is 1 minus cosine squared theta. That whole thing gets squared. Cosine the power of 4 theta sine of theta d theta. And now this is a perfect case for doing a u substitution. Let u equal to cosine of theta. Then du d theta is going to be equal to negative sine of theta, which is right there. So we just have to toss in an extra little minus. So this is going to be equal to minus 1 times the integral of 1 minus u squared u to the power of 4 times du. Right? This is du equals to negative sine theta d theta. So I had to throw in an extra little -1 here to make it identical to this one, and then balance it out with an extra -1. So -1 times -1 is +1. And now I exchanged all of this for a du. That's what this guy is. And there's an extra -1 out here. All right, well then, even though it looks kind of ugly, this is a really easy one now. We just have to FOIL this out, distribute the u to the 4th power, and then we have a polynomial. And polynomials are easy to integrate, right? Good, 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 good. Questions, questions, questions? Okay, so that one should be okay. Where'd it go? What about 15? How do we feel about 15? Maybe letting u equal to the x. It's du will go down in power, so that's good. And letting dv equal to secant x tangent x, I think that would make things easy, right? Since we know the derivative of secant x is secant x tangent x. So 15 should also be pretty easy. Integration by parts. Letting u equal to x and letting dv equal to secant x tangent x. Are we okay with that? 16, 17, and 21. 16. Okay, again, we have this root thing, square root of 1 minus x squared. So that might seem like a pretty good opportunity to use one of our suggested substitutions, right? Just like we did a minute ago. But is there a different way to do this one? If we let yeah, I think that's what we're going to have to do. Let's let x equal to sine. Letting we get the sine, we end up with 1 minus sine squared, which gives you cosine squared, which just gives you a cosine in the denominator. And then we'd end up with sine squared in the numerator. And then we take the derivative of that. We'll end up with an extra cosine in there for the dx, and that should work out. Okay, so number 16, try letting x equal to sine of theta, and that should lead to good things happening. Does that make sense to people, or want me to spell some stuff out? Okay with that one?
Which one?
Number 16. Letting x equal to sine of theta should be the key to this one.
Mm-hmm. Yeah, that one's good. Yeah.
That one's good, okay.
Yeah.
What else did I assign? 17, 21. What about 17? Right off the bat, I'm thinking of this as a multiplication of two functions, right? I have t times cosine squared t, so that's my first thought. So maybe integration by parts would be useful. If I did that, the u could be a t, then that means that I would reduce the power of t. That's fun. But then something whose derivative is cosine squared, that might not be as fun. So let's use the power reducing function first. Power reducing function of cosine squared. So we'll end up with 1/2 1 minus cosine 2t. If we distribute, then we'll have one simple integral that just has a power, a t variable, and another integral that has a t and then a cosine function, and then we can use integration by parts, and that should be doable there. Did that make sense for this one? Maybe I should just kind of get started on that one. This is Chapter 7, Section 5, number 17. We have the integral from 0 to pi of t cosine squared t dt. Okay. So let's integrate from 0 to pi of t, and then I'm just going to replace my cosine squared t using my power reduction formula of 1 minus cosine 2t over 2, which is the same thing as 1/2 minus 1/2 cosine 2t dt. And then when I distribute this, I'll get the integral from 0 to pi, and there's a 1/2 t dt minus, and then there's another 1/2 integral from 0 to pi, and there's a t cosine of 2t dt. Good. Now for this part here, we can use integration by parts. Let u equal to t, let dv equal to cosine of 2t, then du dt is equal to 1, therefore du equals dt. And then here, integrating dv equals to integrating, dt here, integrating cosine 2t dt. I think we're getting some mic interference there. If you guys don't mind muting yourselves until you have a comment. So then we have v equals 2, and then this is going to be equal to sine 2t, and then there's an extra 1/2 that goes in there. Right, so the derivative of this is going to give me that cosine. Good, 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 good. And so we end up saying that this part here is going to then be equal to, so let's leave this alone for now, t dt, and going from 0 to pi minus 1/2, giant bracket, and then instead of this integral, we'll end up getting t times 1/2 sine of 2t evaluated from 0 to pi minus the integral of these two. It's going to be equal to 1/2 sine of 2t dt from 0 to pi. Good. Any questions about that setup? You can keep going from here, right? Keep going. Questions, 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 questions? Nope. Nope, 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 nope. All right. There was a little mic interference, so I muted you guys. Any questions? Feel free to unmute yourself if you have a comment. No. Okay, what else did I assign? 21, 22, 26. What's 22, 26 like? 22, 26. 22 looks ugly. What do we do there? Any thoughts on number 22? Looks kind of ugly, but maybe not so bad if we let u equal to the 1 plus ln x squared. Its derivative is going to be equal to ln x over x, which is going to be here with 2. It's going to be a constant. So this right here will end up being the derivative of this part in here. So just a straightforward u substitution, letting u equal to this part in here, the 1 plus ln x squared. Good. So 22, 26, 26, 42. Well, I mean, just looking at it right away, we think partial fraction decomposition, right? So let's see. First of all, the power of the numerator is smaller than the power of the denominator of the polynomial. The degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator. So it's a proper rational function. So we don't need to divide it first. Next, go ahead and factor out the denominator, and then we have to do partial fraction decomposition to figure out how to separate this. Once we do that, then hopefully we get several easier integrals to do, right? So we'll break up this one big ugly integral into maybe 3 or 4 different integrals that are each easier to do, right? That's the hope. We're okay with that? Yes. Okay, I think the next one I assigned was 42. 42, 44, 42. Okay. 42, 42, 42. What are we thinking on 42, 42? 42, 42, 42. If we, this is similar to one we saw earlier. If we had an x squared plus 1 in the denominator, right, remembering that the derivative of tangent inverse of x is going to be 1 over 1 plus x squared, if there was a plus 1 in that denominator, that would make life a little easier. Fortunately, it's not there. So try integration by parts. If we let u equal to tangent inverse of x, its derivative will be 1 over 1 plus x squared. If we let dv equal to x to the negative 2, then we'll end up with 1 over x. And then when we integrate those guys, we'll end up with something ugly. Let's get started on 42. Unless you guys have an objection. It seems kind of ugly to me. Did somebody do it? Is it okay? Anybody? So chapter 7, section Sec5 number 42 has the integral of tangent inverse of x divided by x squared dx. So let's try letting u equal to tangent inverse of x. Therefore, du dx is equal to 1 over 1 plus x squared. So du equals to 1 over 1 plus x squared dx. And then we're going to let dv equal to 1 over x squared dx. And so the integral of dv, 1 dv, is equal to the integral of x to the negative 2 dx. Right, so this is just going to become negative 1 over x, negative of this. Well, I'll just write it as x to the negative 1. Becomes v equals to negative 1 times x to the negative 1 power. Right? The derivative of this becomes positive. Minus 1 becomes that guy. Okay, so then this becomes equal to, we have tangent inverse of x times negative 1 times x to the negative 1 minus the integral of, and then we have these two, so negative 1 times x to the negative 1 times the 1 over 1 plus x squared dx. All right, so let's simplify that. This is the same thing as negative 1 over x squared, x to the power of 1. So this is just going to be negative tangent inverse of x over x plus, and then this is the integral of 1 over x times 1 plus x squared dx. Right, so being careful here, this minus and this minus turned into a plus. Right, this minus is right there, so it became negative 1 times tangent inverse. And then the x to the negative 1 power from there and the x to the negative 1 power from there, each one of those I rewrote as 1 over x. So it's 1 over x times tangent inverse of x, 1 over x times that guy. Okay. This is an indefinite. Okay, so now this guy is still kind of ugly. So I think we're gonna have to do integration by parts to this guy now in order to separate it and come up with fractions. So let's go off onto the side here. A little side work here and figure out what this is. We have 1 over x times, and I'll write it this way, x squared plus 1. That's just this. So this has to be equal to some fraction with an x, and there's a constant in the numerator, plus, and then the other one is going to be x squared plus 1. Now, this cannot be factored any further. If it was x squared minus 1, we know it factors, but because it's an x squared plus 1, we know that in order for this to factor further, we'd have to go into the imaginaries, right? The 0 of this is an I, or a negative I. And so because this is an irreducible quadratic, that means that the constants above form a linear constant like this, right? So there's a constant a there, a b, and a c that we have to find. Good. Okay, now multiplying both sides by the denominator, we end up getting that the left-hand side is just going to be 1 equals to a times x squared plus 1 plus, and then I have bx plus c. What the heck? Stop doing times c, and then all of this times x. Is that okay? I'm kind of skipping a few steps. This is a x squared plus a plus bx squared plus cx. Good. Questions? Okay, so we group them up by powers, and we end up with a plus b must be x squared, and the c times the x, and then plus a. And looking on the other side, I can add the other powers. So there must be a 0 times x, and there must be a 0 times x squared. So now x squares match up with x squares, the x's match up with the x, and the constant matches up with the constant. So I can easily conclude that the a must be a positive 1, for sure. It's the only constant. Good. I can conclude that the b must be negative 1, because it must be true that a plus b equals to 0. Right? A plus b, this part must be the 0. And the a was a 1, plus b equals to 0. Therefore, b must be negative 1. So I have 2 down. And the last one here is another obvious one. Because the c in front of the x must be that guy, well, we also can conclude easily that c must be 0. So c must be 0, a is a 1, and b is a negative 1. So coming back over here, this is a 1, this is a negative 1, and this is a 0. So going back over here, I end up with negative tangent inverse of x over x plus the integral of 1 over x, and that looks like it's a minus, so I'll say plus minus x all over x squared plus 1 dx. Good. Questions? Okay, so then this becomes, I'm just going to rewrite it as negative 1 over x times tangent inverse of x plus the integral of 1 over x dx minus, and then here I'm going to do a little u substitution. I'm going to let u equal to x squared plus 1. So du is going to be equal to 2x dx. So I almost have it. I just have to throw in that extra 2 times 2 and then balance it out with a 1/2. So I'll end up with minus 1/2 on the outside of the integral of, and then 1 over u du. Good. So these are actually very similar. And so this is negative 1 over x tangent inverse of x plus ln of x, absolute value of x, minus 1/2 ln absolute value of u, plus a constant. And the u was really equal to this. So we have negative 1 over x tangent inverse of x plus ln absolute value of x minus 1 over 2 ln of absolute value of, that becomes x squared plus 1 absolute value plus some constant. Good. Okay. Well, we could leave it alone like this, or we could manipulate this a little bit, because I know that the book likes to combine the log terms. So to combine the log terms, I'd have to write it like this. Tangent inverse of x plus ln absolute value of x. I'm going to put plus ln absolute value of, and then x squared plus 1 raised to the power of this minus 1/2. I'm going to raise it up to the exponent. Remember, that's one of the properties of logs. I can take the little exponent and move it out in front, or I can take it and put it up in the exponent. I can go back and forth with it. Good. Good. So this minus is the same thing as flipping it upside down and taking the root of it. So this is -1/x tangent inverse of x plus ln of absolute value of x plus ln of absolute value of 1/x squared plus 1 in a root plus some constant. And now when we have the summation of two logs with the same base, then we can bring them together by multiplying them and get one big happy log. So we can rewrite it as -1/x tangent inverse of x plus ln of absolute value of x over the square root of x squared plus 1 absolute value plus c. I think that's as good as it gets. Any questions about this question, this problem? We're good. So we start off with a nice straightforward integration by parts, but then that leads to this ugly thing. So then we have to separate it using partial fraction decomposition, and then do a little bit of algebra to simplify our final result. Good? Questions? No? My computer is struggling to keep up with all of these programs, so now it's not responding. There we go. Okay. 56, 60, 71. Is part of that. What do you guys think about 71? What should we do there? Anybody get that far? Any questions or any ideas on what to do with number 71? Why don't we start off by letting u equal to e to the x. U equal to e to the x. Then we can solve for x. U equal to e to the x, then ln of u equals to x, then you can find the derivative of x. Yeah, that should simplify into something good. Did anybody do number 71? Is that what you did? Let's see what I have. Chapter 7, Section 5, number 71. The integral of e to the 2x over 1 plus e to the x dx. So let's try something here. Let's let u equal to e to the x. So first thought is, okay, well, if I do that, then d dx of the u is equal to d dx of the e to the x, right? And so we end up with du dx equals to e to the x. So du equals to e to the x dx. Which means that the integral of e to the x, e to the 2x is equal to e to the 2x is equal to e to the x squared. Is equal to e to the x times e to the x. So I can use one of them to be this and one of them to be u. Like this. So then this guy could be my du. And then I end up with u over 1 plus u. U and u. End up with the integral of u over 1 plus u du. Okay? So, I'm going to rewrite this, rewrite it the other way around. U plus 1 du. And now they have the same power. Right? So I can separate these a little bit. And, you know, another trick for these, a lot of people have discovered this little trick. I can do plus 1 minus 1. And then I can kind of group these up and say this is group, and that's a little group there. So I can separate this as the integral of u plus 1 over u plus 1 minus 1 over u plus 1 du, which then becomes the integral of 1 minus 1 over u plus 1 du. Good. Good. Questions? So then this just becomes u from here minus ln absolute value of u plus 1, absolute value, plus some constant. And so finally the u was equal to e to the x. So this is just going to become e to the x minus ln absolute value of e to the x plus 1 absolute value plus some constant. Good. Okay, well, you know, that's just a little touch of the homework. They're really hard. Just try different things. it's quite possible that you run into a brick wall, try one thing and it doesn't work out, to just back up and try something else. Any questions on this one? Yep. No.